Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part 2 of the Unconventional Fuels segment. In part 2 we will discuss tar and oil sands, the energy return on investment of unconventional fuels, the upgrading and refining and related environmental issues of unconventional liquids, and we will discuss methane hydrates.
Let's first look at a forecast of unconventional liquid fuels use in the US. This is a graph from the Energy Information Administration's Annual Energy Outlook from 2014. It predicts liquid fuel use up to the year 2040. And so you see here that crude oil production, so this is conventional liquids production, remains fairly constant. We're coming off the peak in the 70s, but due to the recent revolution in production methods of unconventional sources, we're having a strong uptick in unconventional liquid fuel sources. The uptake is predicted to end already close to 2020, so we're already slated to go through another peak in liquid fuels production. So this can only be regarded as a short-term relief. The impact, of course, in that near term is that the imports of liquid fuels, which is shown blue here, that is of course dramatically reduced. But as time goes on after the peak, the imports will go slightly up again. There is a main decline in liquid fuel use in the forecast because of efforts made to make cars more efficient and so forth. So what are oil and tar sands? When you think of oil, then you think of a liquid. But oil and tar sands rather contain bitumen. And bitumen is a solid that is a mixture of primarily polycyclic aromatic hydrocarbons. What you see here is a selection of such polycyclic aromatic hydrocarbons. You see that they contain these rings. When you think of gasoline or any liquid fuel really, it's more linear chains of hydrocarbons. And so it is clear that if you want to make fuels that are compatible with existing machinery, this bitumen needs to be refined heavily to convert it into linear hydrocarbon chains that can be used as liquid fuels. So where do we find the bitumen? There are two principal ways to mine it. Some oil sands deposits are close to the surface, and they talk about if it's up to 100 meters down, they can do direct strip mining. So they remove the topsoil and then they recover the bitumen and then they can extract it and process it. If it is deeper down, below 100 meters, then it is not economically feasible to do strip mining. And then, of course, you can imagine, as we saw now, it is a solid. We need to somehow liquefy it that we can pump it to the surface. For that, they use SAGD, which is steam-assisted gravity drainage. And essentially what they do there is they pump hot steam underground, and then they liquefy the bitumen and then they can suck it up to the surface for further processing. Let's go to the Total website. Total is a major player in tar sands, and they have some pages where they discuss the technology. That's also where I took this figure. And let's look at their videos that explain how these technologies work. So this one is about the SAGD, the in situ recovery.
For deeper oil sands deposits at depths of more than 100 meters, the high viscosity of the bitumen must be reduced to make the bitumen mobile enough for recovery. Among other possibilities, the method most frequently used is steam injection, in particular a technology called SAGD, steam-assisted gravity drainage. An on-site unit produces steam that is injected into the oil sands reservoir. The recovered bitumen then goes through several separation processes before it's piped to a refinery. Two horizontal wells are drilled, one above the other and about 5 meters apart. These wells can be up to 1,000 meters long. From the upper well, steam is continuously injected into the oil sands layer. Softened by the steam, the bitumen flows into the lower well under the effect of gravity. From this well, the bitumen is pumped to the surface, mixed with the condensed water. Above ground, the bitumen is separated from the water by adding a diluent. The water is treated and recycled to produce steam. The water is treated in water softening facilities and sent back to the steam generators, boilers using natural gas. For water makeup, brackish water is used, which is first filtered and treated. After further addition of diluent, the bitumen is transported by pipeline to a refinery or an upgrader for conversion to lighter products.
So it's pretty obvious that this process uses a lot of energy and also water. The heating of the steam is of course the main energy input, and you saw it, they're using natural gas for that. So let's look at the open pit mining video.
Oil sands at depths of less than 100 meters can be recovered by mining using open pit mines. First, the topsoil is removed. This soil is stored for future land reclamation. Next, the overburden covering the oil sands is removed and stockpiled for use as dikes and backfill. The oil sands ore is then dug out of the mine using shovels. The raw ore is transported to crushers by truck. The ore is crushed into small pieces about 5 centimeters long. Water is added to prepare a slurry that can be transported by pipeline. In this phase of transport, called hydrotransport, the bitumen starts to separate from the sand and finer particles. The slurry of water, bitumen and sand is piped into large separators. Coarse sand and some tailings are collected from the bottom. A froth composed of bitumen, fine tailings and water is skimmed from the top. This gravity separation is assisted by injecting air, so the bitumen particles rise to the top more readily. Deposited in the open air, coarse tailings form sand beaches and gradually dry. By adding a solvent, the froth is separated into 2 parts. One part is water containing fine tailings which are treated in a tailings pond. The other part is bitumen. After adding a diluent, the bitumen is ready for transport by pipeline. The bitumen is sent to a refinery or an upgrader for conversion to lighter products.
With this technique, the main issue is probably the big pit that is being generated, and it's probably also costs a lot of energy to remove all that topsoil, and then there is of course the water use. This shows a schematic of the steam-assisted gravity drainage SAGD process, and you see it's very similar actually to fracking. The problem is that the fuel is not recoverable, because it is stuck in its geologic formation, and so we need to somehow do something to it to be able to get it above ground. And so in this case, because the bitumen is a solid or has a very high viscosity, we need to make it liquid, and so the trick here is to heat it up and thereby liquefy it. And that means we have to heat the entire volume around the steam pipe, and then we can extract whatever volume we can heat up. And the gravity comes in because it drains into that bottom pipe that is below the steam pipe, and so gravitation helps to drain the liquefied bitumen into the extraction well. Similar to the fracking process, this also means that we have to build many of these wells if we want to access the entire resource. The main issue with this technology is that heating is energy intensive. This causes in turn a low energy return on investment. There are studies that claim that this technology has only an EROI of 2 or 3. This would mean that in the extreme, 1/3 of the energy extracted would actually be lost for the extraction process. Once the bitumen has been extracted, it needs to be upgraded. Because bitumen is a mixture of long-chain hydrocarbons, liquid components, and small volatile components, we need to go through a step-by-step process to separate and then process these individual components. The first step usually is atmospheric distillation, which at slightly above atmospheric pressure removes small volatile components. This is followed by vacuum distillation, where liquid components are extracted. The remaining long-chain hydrocarbons, they are cracked in a coker, so they are essentially heated until they break up, and then we get smaller molecules, shorter chain molecules that are liquid or in gas form, and we get a residual which is called coke, a coal-like substance that can be used as fuel. And then finally the extracted liquid and gases are being hydrotreated with hydrogen. So it's again, everything is heated up to a fairly high temperature, 300-400 centigrades. And hydrogen is added, and that removes sulfur, oxygen, and nitrogen from the hydrocarbon chains and replaces them with hydrogen. That stabilizes the fuel and turns it finally into a standard synthetic fuel that can be used in standard equipment. So every single step in this process requires heating up the hydrocarbon mixture, and of course that costs a lot of energy. That is the other factor in the low EROI of about 1 to 2 or 1 to 3 of this technology. A similar situation presents itself with regard to shale oil. Shale oil is found in similar geologic rock formations like shale gas, and the hydrocarbon that is embedded in the shale is kerosene. We have the same problem with kerosene because it is a long chain, high viscosity substance, and this kerosene can only be extracted if it is liquefied. And so in this case, they heat it to a temperature that it cracks into more liquid components. So we're doing essentially cracking directly on site underground, and that again requires large amounts of heat. That is done with steam, or there are some experiments underway to use electrical heaters for this process. Think of that. First we lose 2/3 of the energy to make electricity, and then we use that electricity to generate heat underground to extract oil. Let's have a quick look at kerosene. Kerosene is a high-weight hydrocarbon which is composed of a mixture of a large number of different hydrocarbon monomers. You see a possible structure here. So we have all these individual compounds that are linked together, and all this creates a solid waxy material. You can imagine if this gets cracked, we get a large number of different fractions that have different liquidities and viscosities. It is obvious that this type of material also needs a lot of post-processing, refining before it can be used as a fuel. Now we know that unconventional fossil fuel sources are more difficult to extract. It costs more energy to extract the energy from the ground. That means the energy return on investment number gets smaller and smaller. In turn, of course, that means that it gets more expensive to extract these fuels. There are studies that investigate the connection between EROI and the marginal production costs of oil. And we see a graph here. That's the production cost in dollars, 2007 dollars. And this here is the EROI that is associated with these production costs. And so you see here that, for example, in Saudi Arabia, they have a very good EROI. It's here still at around 40. It costs only a little bit more than $20 to get a barrel out of the ground. And so if you can sell it for $90 or $100 like currently, then that means you can make a really good profit. But if we go to a lower EROI, let's here look at the global average. Already it doesn't look so good, right? It costs 40, so you can only double or triple your money. And if you go to ultra deep sea drilling or oil sands, the price is really close to what oil is selling currently. So this means that these technologies are really only attractive if the oil price is high. Now, if you combine the oil price with economic performance, we know this. Average price of oil during recessions is around $70 or higher, and the price during expansions is below $40. So that means if we are left with only low EROI sources, once the conventional sources are all depleted, that cannot be good for the economy, because more and more effort will go into finding energy, and less of the energy that is being produced can be used by society, because more and more has to be plowed back into the energy finding process. And so the degradation of the EROI over time that we are observing right now, already the last decades, the EROI has been going down, the global average, and it can only go down further because the easy access fossil fuel sources are about to be depleted, and only the more complicated, more energy intensive sources remain. And so we have to accept the fact that it will get more expensive to get these fossil fuels. If there is an environment of declining EROI, there are two ways to deal with this degradation of the EROI. This slide shows one way. We see two scenarios. This is the current scenario. The EROI is 18, that is the global average approximately right now. That means 6% of the energy is lost to the extraction process and 94% reach society, and that seems fairly acceptable. If the EROI goes down to 1.2, an extreme case that could be associated with biofuels from food crops, then 80% of the energy is being fed back into the production process, and only 20% of the energy actually reaches society. Now, we saw on the previous slide that if this happens, the price of the resource will go up dramatically, and that will of course motivate people to quench their thirst for these fuels, and they will invest in high mileage cars and insulate their houses better and so forth. So this is clearly the intelligent way to deal with the situation of degradation of the EROI of fossil fuels. We start using less and we find alternatives to provide energy. The alternative to this scenario is of course that we simply keep going and we continue using as much fuel as we do right now. But then if the EROI is reduced, we have a scenario like this, that the extraction needs to be ramped up dramatically in order to continue providing the 100% of fuel to society. Obviously this is not a solution, because the Hubbert peak will turn into a Hubbert cliff, because as we go through the peak and it gets more difficult to find the resource and the EROI goes down, we use more and more and more, and so the decline here gets accelerated. Let's talk about environmental impacts of unconventional fuels. If you consider the extraction process for bitumen, remember there was a lot of water involved. We use steam to liquefy it and get it out of the ground. It is being transported in pipelines as a slurry with water. And so the issue here is that bitumen, which is a mixture of many different hydrocarbons, contains a certain amount of hydrocarbon acids. You see here some typical structures. So they have these carboxylic acid groups attached to them, and these are polar, and that makes these compounds soluble in water. So in other words, this means that the water that is being used for the extraction process is being contaminated with these compounds, and these are all aromatic, and so many of them are harmful. This water, of course, ends up in those tailing ponds that were mentioned. That these compounds are toxic, this was demonstrated by 1,600 birds that died in a tailing pond of Syncrude, which is a major oil sands company in Alberta, in 2008. Right now there are about 170 square kilometers, 66 square miles of tailing ponds in Alberta, And of course, as we ramp up the tar sands and oil sands extraction, this can only get bigger. Another environmental concern is pollution from upgrading. Remember, during the upgrading process, we go through several stages of heating the bitumen and its components. And so during all of these processes, some gaseous compounds are being produced, and some of them get emitted into the atmosphere. And then together with rain and wind, these compounds get distributed around these facilities. This figure is from a study by Kelly et al., where they investigated the contamination around one of the major oil sands producing areas in Alberta. You see it here on the map, so it is in the northern part of Alberta. And what they did is they went around these production sites and collected snow samples in this region and then analyzed the amount of bitumen-related compounds in these snow samples. And so this region goes from Fort McMurray to Fort Chipewyan, and we will see now on the next slide how these snow samples came out. On this slide you see the filter pads through which melted snow was filtered. So they took some snow, melted it, and then let the meltwater drip through filter pads. And then they put the filter pads on the lab bench and arranged them in a pattern that conforms to the locations where they took the samples around these tar sands producing plants. And you see here clearly that the further away you go from the epicenter of tar sand production, the filter pads start looking a little bit lighter, and close by here they get really dark. Then they took these filter pads and they analyzed the chemical composition of this black deposit, and they found that there is a significant amount of polycyclic aromatic compounds in these deposits. So this clearly shows that these production sites emit aromatic compounds and that they are introduced into the environment. An additional study analyzed the water in this Athabasca River that goes to Fort Chipewyan, and they measured toxic concentrations of related substances that are toxic to the fish in this river. Yet another environmental concern is strip mining. Here you see a typical picture of such a mine. Strip mining means that the topsoil is removed up to 100 meters, and that of course has the consequence that the natural environment is entirely destroyed. Let's see what the Canadian government has to say about this. I surfed here to the oil sands webpage of the Albertan government. Let's see what they have. It seems there is a movie, so let's have a look.
This used to be a tailings pond. If you were here 2 years ago, you wouldn't be able to drive across it. So we've been reclaiming this pond for the past 4 years. So far we've planted 150,000 trees. It's probably about this big when it was planted, so it's grown quite a bit. We have 450,000 more to go.
Just over this hill here was actually a big hole in the ground. It was one of the first mine pits that we had at Syncrude. The trees are 15 to 20 years old that were reclaimed that long ago. And then there's other areas where it's quite a bit younger. Some of the trees down there are between 5 and 10 years old.
Reclamation is a pretty complex activity, actually. It starts with detailed planning from before a project even gets started, and it goes all the way through mining and operations through to closure. All the operators have a requirement to reclaim everything that they actually disturb for mining. So whether it's a mine pit or a tailings pond or an overburden disposal area, our goal up here in the oil sands is to make the landform sustainable and the drainage is functioning and appropriate and last a long time.
My experience in the oil sands is learning better ways to do things. 10 years ago, when we were doing consultation with First Nations elders, they told us if we took that forest floor layer and put it in an area that was ready for reclamation, then it would speed up our reclamation process.
One day this will look like a really nice wetland with some rolling upland hills. Woody debris provides wildlife habitat and provides...
Well, beautiful. So it seems everything is well under control. Let's have a look at their map down here, what we're talking about. This is in fact the very same area like what was discussed on the couple slides about pollution. And so on the scale of Canada, of course, this is just a tiny little speck. In total, it is 4,800 square kilometers, about 767 apparently have been already mined. And the forest that has been disturbed is 0.2% of Alberta's boreal forest. So about boreal forests, one thing should be known. They take a very long time to recover, and so what they're planting there, of course, will not be like a boreal forest for quite a long time. It can take hundreds of years until the original environment will be restored again. So again, something to think about when talking about unconventional fossil fuels. The final part of this unconventional fuel segments is about methane hydrates. It can be considered the final fossil frontier. If we run out of everything else, then this is what's left, and apparently there is a vast amount of it. However, it is at the bottom of this unconventional fuel pyramid that we saw at the beginning. So that means there's a huge volume, but it's also probably very difficult to extract. And so here we have an interesting graph that shows how methane can be dissolved in water depending on the pressure and the temperature. There are essentially two ways that methane can be in water. It can be just simply dissolved at high temperatures and low pressures. So this is essentially what we get through the fracking process when methane enters the water table, and then we have contaminated water coming out of the tap. If the temperature gets lower and the pressure gets higher, like you would find it deep undersea or in very northern regions, then you can get methane hydrate, either in water or in ice. And methane hydrate, that means that the methane molecules are within a cage of water molecules that form a structure around the methane molecule in the center. So if it is in ice form, then we get what some people call fire ice, because one can set it on fire. So just looking at this graph, we can already predict that it will be very difficult to extract the methane hydrate, because it will be either at very high pressures or at very low temperatures. So it means going north or deep. This is shown here. On this schematic, we can find it either below the ocean floor, where the water layer is very thick, so we get a high pressure down here, or we can go further north, and there we can find it closer to the surface because it is cold. Methane hydrates have been already a focus of research for a few years. Here you see an aerial shot of the Mallik exploration site in the northwest territories of Canada. I googled it, you see it down here, so close to Alaska. In this site they drilled a hole to access one of those underground methane hydrate reservoirs that can be found in cold regions. This here shows the experimental setup. They used the so-called depressurization method. And this works by pumping out water from the borehole, and that lowers the pressure down here, and this lowering of the pressure then releases the methane. So what happens in their experiment is that after 60 hours, sand invasion here from the surrounding areas around the borehole stopped the experiment, and they got 12.5 hours of optimal operation, and that produced 830 cubic meters methane, which they flared off. So this experiment shows that I guess one can get at frozen methane hydrate in northern regions. Here you see the methane hydrate resource pyramid. The previous slide, the experiment that we saw there, that exploited Arctic sands. So we're here at the top. So this is the low-hanging fruit, the most easily extracted methane hydrate. Now there are vast resources that contain a lot of methane, and if you look at these estimations here, if one really could get at this methane, one would have enough methane for hundreds of years. However, most of this methane is trapped in muds, and they have a very low density of methane hydrate, and so it will be increasingly complicated and expensive to access. And of course, whenever something like this is discussed, always keep the EROI in mind. Compare it with the EROI of Saudi Arabia, where it is really easy to get oil out of the ground, and think of the effort that it would take to extract a low-density resource in northern climes of this nature. This brings us to the end of the unconventional fuels chapter. Let's summarize. It is clear that unconventional resources amount to a large reserve, which could easily give us another 100 years of fossil fuel-based energy. It's also obvious that improved technology will enable access. However, the issues are high cost, low energy return on investment, EROI, which has the potential to stifle economic growth. And there is, of course, also a significant environmental risk. You saw it takes a lot of water, there is air pollution, and there is the disturbance of vast regions of currently pristine natural environments. This concludes part 2 of the unconventional fuels section. Thanks for watching.